Welcome to this video on solving right triangles. This is section 2.4 from our textbook. Uh, the objectives are to cover significant digits. Then we're going to talk about the kind of principles behind solving right triangles. And then we're going to look at a few word problems. Well, hold on, we just have the one problem right here. Yeah, we're going to talk about angle. We have to define angles of elevation and depression. And then we've got a word problem. Pretty standard type of word problem. All right, so let's go back up to the top here. We've got our significant digits. Significant digits are found by just counting the number of numbers that occur. The only thing that's weird here is zeros. You only count zeros that are either to the right of the decimal place. Hopefully you can see my cursor. So zeros after the decimal or zeros that are between other numbers. So I've got a bunch of examples for you down here. 408, that zero is between 4 and 8. So we count the 4, we count the 8, and we also count that 0 since it's between two other digits. So it's got 3 significant digits. A number like 400 only has one significant digit because these zeros are not between two other digits and they're not to the right of the decimal place. So it seems a little weird. So a lot of people will say that trailing zeros don't count unless there's a decimal place. For example, 8700 has these two trailing zeros. We don't count them. We just count the 8 and the 7. However, if there's a decimal there and we throw in a number after that decimal, we do count the preceding two zeros. So 8700.1, we count all of those digits to get 5 significant digits. What if, idea here, what if we had, I don't know why that dot appeared. What if we had like, say, 87 point, oops, I don't want my decimal there. Let's say 8700.0. So the question is, do we count these two zeros? Do we count these two zeros here? Yes, we do. Because we have to count the 0 after the decimal place. And since we're counting that and we're counting the 8 and the 7, these two zeros in the middle are occurring between digits that we count, so we do include them. This would have 1, 2, 3, 4, 5 as well. Oops, wrong button. So this is a new program for me. Very exciting. So I would have 5. Neat. All right. So we skipped a few. We skipped the last one. 2.00 has 3 decimal. I don't know why this little dot is there. All right. So when performing a calculation, the result is only as accurate as the least accurate measurement, as determined by considering the number of significant digits in each measurement. So we're being asked in this first example, example 2, to calculate 7.02 times 8.296. We count the significant digits in each. 7.02 has 3 significant digits. 8.296 has 4. So the least accurate of these is 7.02 with 3 significant digits. So our answer is only going to have 3. So we multiply those together and we get 58.2. I don't have my calculator right in front of me. There was some rounding here. We had to round this. Just in general, I would say, in this class, and really in general, when you're doing your calculations, when you have to make multiple calculations, just carry on a few extra significant digits. So if your least accurate has 3, your most accurate has maybe 4, I would say during your calculations, maybe write down 5 or 6 decimal places. But make sure you carry a few extra or you're going to encounter rounding errors. The other way to do it is just not do any rounding until the very end. So that's what I always told. Don't round until the very end of your problem. I will tell you something slightly different. You can round, but keep a few extra digits. If you know your answer is going to have 3 digits, then I would keep at least 4, preferably 5 significant digits throughout your calculations. Now, another really exciting thing that no one ever told me growing up, and it really bothered me because it's super important. Significant digits only concern real world measures, not numbers resulting from counting or theoretical work. I'm going to give you an example of this. Well, you can see right below here, we're talking about some apples. So if you have a number like 13 apples, we call this a discrete number, right? This is a discrete amount of apples. We're not going to be talking about this is a person buying apples at the store. You're not going to go to the store and buy 0.25 apples. It's just not going to happen. They're going to kick you out of the store if you start cutting up apples. So you're going to have a whole number of apples here. There is no significant digits for this. So 13 apples, we don't even care. Significant digits do not come into play at all. The only thing that matters is the significant digits of this, because this is something that's measured by the scale in the store. And as I do here, that's pretty accurate for a store scale. So I wish someone had told me this. This was very frustrating and confusing to me growing up. So hopefully this helps you out a little bit. When you're talking about significant digits, counting does not come into play. If you have some number in your formula says like 2x, and you've got some value, some measurement you're plugging in there for x, that's the measure that matters. But like again, if your formula has something like 2x, that whole number that's not coming from a measurement, it's just in your formula, does not play in. It doesn't count at all when you're talking about significant digits. So sorry for the rant, but it was something that bothered me for a long time, and we didn't have the internet. I imagine a lot of you know what that's like growing up without that and not being able to look up these things. Side note, now you can. So if you ever get confused and can't get a hold of me, Google it. Sorry, lots of tangents today. I've had too much coffee, I think. So looking at this, Jill calculates the average weight of each of her apples is 5.281 ounces. She has 13 apples. How much do they weigh altogether? So we count 5.281 has 4 significant digits, which is pretty easy to figure out since there are no zeros. We just count the 4 digits. 13 is an exact count of these. We can disregard significant digits for that. So the only thing that plays in here, the only thing that counts is these 4 significant digits. So our answer should have 4. So we multiply 5.281, the average weight of our apples, by 13, the number of apples we have, and we get 68.65. And again, there was some rounding here. I wish I'd written the extra digits and we just rounded to 4. Okay. Now on to the meat of this section. Okay, I say that. One last thing. I'm not hugely concerned with significant digits in here. I've never been a stickler for them. So if you get an issue in your work where, like on a test or something, where you're off by like a decimal place, just let me know and I can fix that. I may laugh at you a little bit. No, I wouldn't do that. Maybe I would. So solving right triangles. There's so many deep maths in here that's very exciting. This is a great, what we're going to talk about here is generalizable to any mathematical formula you encounter in your life. So our trig functions relate 3 things, 3 variables, 3 pieces of information. In our case, the trig functions are 2 sides to 1 angle. For example, sine of an angle is equal to the opposite side over the hypotenuse. So we have 3 pieces of information. We have the angle, we have the length of the opposite side, and we have the length of the hypotenuse. Here is your big generalizable rule. If you have 3 variables, if your formula has 3 variables, you're going to need to know what 2 of those are in order to solve this thing. So if you know the angle, If you know the angle and you know like the opposite side, then you could solve that for the hypotenuse. If you know the opposite side and the hypotenuse, you could solve for the angle. If you knew the hypotenuse and the angle, you could solve for the opposite. So there's your rule, very powerful rule for mathematics. However many variables you have, you need to have a number to plug in for all but one of them. Most of the time. There are situations where you can do it without, but that involves combining multiple formulas. We're not there yet. You probably did that in an algebra class at some point. You would use either the, gosh, for the rules, we use the substitution method, or you would add the two formulas together and try to cancel out. Okay, but that's neither here nor there. Okay, so in order to solve our trig equations or our trig formulas, we need to choose the formula that matches the data that we have, right? So we want to pick a formula for which we have two of those values or two of those pieces of information, and then repeat and repeat and repeat. This is what trig was all about. Finding these relations between angles and sides. This is what people did with trig for the longest time, and it's still probably the most valuable thing in trig for a lot of people. This is the kind of thing I use when I'm working on some woodworking project. I'll use these rules to figure out my angles, my sides, etc. One other thing, super nice rule, the angles must have a sum of 180 in a triangle. I think I should have the word triangle in here. Just random angles out in the wild, don't have to add to it. And it looks like I started repeating that line, so I'll just scratch that. I'm borrowing this laptop with a fancy pen that lets me write on the screen, and I'm okie dokie. So let us look at this triangle they've given us. They've given us an angle. They've given us the angle capital A here. And the angle is 34.5 degrees. They've given us lowercase c is 12.7, and that's the hypotenuse of our angle, of our triangle. So some things as you get into solving right triangles, some things you want to take note of. Our angles A, B, and C are all capitalized, and then we use lowercase letters for the sides. And this is a standard thing. If you ever want to look something up online, you go to just Google this stuff. This is a pretty common standard, so you should see that everywhere. This is really convenient. If I see a lowercase a and a capital A, I know that that lowercase a is going to be the side opposite of my angle capital A. All right, so now that we've talked this triangle to death, let's look at one of our trig functions that relates these together. And fortunately, just by coincidence, I've written one of those right here. If I have an angle and I can relate that angle to the opposite side and a hypotenuse. And looking at our triangle, my angle 34.5 degrees, I don't know the opposite side, but I do know the hypotenuse. So once again, I know the angle, I know the hypotenuse. The only bit of information I'm missing is that opposite side. But we've got two of the three values to plug into our formula, and that's more than enough. In fact, it's the exact amount we want. So let us take our definition of sine and plug in these values we have. So sine of 34.5 degrees is equal to the opposite side, which we're going to call our lowercase a, because that's what they labeled it as, over the hypotenuse, which is 12.7 inches. So how do I solve this for a? It's super simple. What I want to do is I want to multiply both sides of my equation here by 12.7. So what do we need to know here? We have on the right side, A is divided by 12.7 and multiplied by 12.7. So these are going to cancel out. Like if I multiply something by 2 and then divide it by 2, I haven't really done anything. Right? Those two things cancel each other out. So I'm going to cancel these out. Alrighty. So on the right side, I'm left with A. On the left, I've got 12.7 times sine of 34.5 degrees. And I don't have my calculator, which is going to make this interesting. Hold on, let me grab my calculator real fast. You can be entertained by the sleeping dog, who is so patiently waiting beside me. A good dog. Or, you can just fast forward videos. Apparently I can just pause this. Sorry, we're still working on it. I don't see a pause or a stop now that we're... Oh yeah, phone. Smart. Okay, plugging this into my phone. Sorry for that. 34.5. So sine of 34.5 and multiply your answer by 12.7. And I get, I'm setting in radians. Let me change that to degrees. And now it's going to make me re-enter that. Sine of 34.5 times 12.7 Man, that's crazy small. I get 7.19. I'm going to write out a few extra ones. 7.19336. But since I only have 3 significant digits in each of my bits of data, right? The hypotenuse is 3 significant digits. The angle is 3 significant digits. My answer here can only have 3 significant digits. So 7.19. That's going to be the length of side A. Okay. So we could use the Pythagorean theorem here. We could use the sum of the angles. We could use another trig function. I feel like using another trig function. Yeah, let's do another trig function. Let's do cosine here. So I'm going to use the angle I still have. They gave me 34.5. But this time, instead of the opposite side, I'm going to use the adjacent side, B. That would be cosine. Cosine of 34.5 is equal to the adjacent side, B, divided by our hypotenuse, 12.7. So same as before, conveniently, I You just multiply by 12.7 to eliminate that fraction and get b by itself. We get b is equal to the cosine of our angle. Cosine of 34.5. Okay, and then I want to multiply that by 12.7. Okie dokie. What the heck? Why did it fill that in? Use the eraser to erase ink that's been drawn on the page. Well, what do you think I'm doing? Does not want to erase my circle here. Oh well. Super weird. 10.466. Sorry this is so messy. Apparently drawing on the screen with a plastic pen is harder to control than I thought. But again, I only want 3 significant digits for this, so over here I'm going to write 10. What the heck? Why is it doing this? Ink to shape. Okay, that should. I need to turn that off. There we go. Okay, yeah, I can just. It wants me to delete these manually. Got it. Got it. We've made progress. So it is 10.46. Well, I want that third digit, but because the fourth digit is higher than, well, since it's greater than or equal to 5. So anything 5 or greater tells me I'm going to have to round up the digit before that. So I want this third digit. The 6 tells me to round that up. So instead of a 4, I round it up to a 5. Okay. Now, lastly, we could use another trig function to find angle B. But we're not going to, because if you've got one of the angles, and this angle is given to us with this little box here, which means that it's 90 degrees. So we actually have 2 of our angles. When you've got 2 angles, you're going to use this fact that the sum of these has to be 180 degrees in a triangle. So we're going to take our 180 degrees and we're going to subtract the 2 angles we have. Subtract 90 degrees, subtract 34.5 degrees, and that will give us our final angle. Okay. 180 minus 90 minus 34.5 is 55.5. And now we have the last bit of our puzzle. Oh, these aren't the greatest. These are all 5s, believe it or not. Just really poorly drawn. I guess I could have written a step before this. My angles are, let's see, A, B, and C. A plus B plus C equal 180. And what I've done is I wanted angle B by itself. So I wanted this angle B by itself. I subtracted angle A and I subtracted angle C. And that's how I came up with this formula. This formula is just 180 minus angle C minus angle A equals that unknown angle B. So unknown angle B was 55.5, and the other two, C was 90, and A was 34.5. Solve a triangle that has one side of length 29.43 centimeters and a hypotenuse of 53.58. Yeah, we can do this. Yeah, we can totally do this. I should have written here that this is a right triangle. Otherwise, we could not solve this so easily. There are ways of solving triangles without right triangles. If you have a triangle that's not a right triangle, you can still do this, but we will not be doing that for a little bit. So the first thing I'm going to do is draw a triangle. Very terrible right triangle. So I'll say one side has a length of 29.43. It doesn't matter which one we label that. I'll call this one on the side centimeters and a hypotenuse of 53.5. So I have those two. I'm going to relate them to this angle we'll call theta. And conveniently, we're going to be using sine here. I like to start with sine. Sine's my favorite because it's first on our list. So sine of our unknown angle is equal to the opposite side, 29.43, divided by our hypotenuse, 53.58. So our formula, our definition for sine had 3 variables in it. We plugged in values for 2 of those variables. Now we just need to solve this for the remaining variable. And when that is done using the inverse sine function, I'm going to cram this in here. The way we do it is we take the inverse sine function of both sides, although I think no one but mathematicians actually write out this step. When you take the inverse function of a function, those two things essentially cancel each other out and leave you with the argument of that function. It leaves you with our angle there. Okay. On the right, we would have to calculate the inverse sine of this. And again, you could calculate this division. I don't do that. It's a 3 there. This pen, a little harder than I thought to write. You could calculate that. Personally, I don't do any of these calculations until the very end of my problem. Okay. Do, do, do. This is pretty annoying to type in on my phone. Because the calculator that came with the phone doesn't have inverse sine. 29.43 divided by 53.58. Try it again. It's not like this. Okay. Sorry that took a minute. So it's 33.31709, and there's a bunch more decimal places, but we're not going to write all those down. I just wanted to talk about significant digits. All of our other bits of data they gave us were 4 significant digits, so we only want our 4 digits. However, that last digit, the 1, we have to look at the next digit, which is a 7. That tells us to round this up to a 2. So 33.32. Again, anytime the next digit is 5 or greater, and 7 is greater than 5, then we need to round up that digit. So instead of a 1, round that to a 2. Triangle is 33.32. Cram this in here. 33.32. Just like before, I'm not going to use a trig function to find my other angle. I'm just going to use the fact that these things add up to 180. So there was step 1. Step 2 is to take 180 degrees and subtract the angle we just found, 33.32 degrees, and subtract the angle 90 degrees. All right. Minus 32. And I get that this is 56.68 degrees. And finally, we have our remaining side, the adjacent side here of that first angle we calculated. We still need to find that. And let's see. What am I going to call this side? I'm just going to call it x, since I haven't actually named any other variables. Now, we could use this angle 56.68. We could use that. And x is the opposite side of that, so that would tell me I want to use sine. In general, I prefer to use a number that's earlier in the calculation. I'm going to use this 33.32 because that has the least amount of built-in rounding error. Because we rounded that one, and then the 56.68 also had rounding involved. So I'm going to stick with this first angle we calculated. I don't want to keep compounding these errors. Because even if you're really careful with significant digits, I mean, errors are still occurring. That's why we have to take into account significant digits. We want to have a cutoff for where our for what that error is going to be. We have to sneeze. Excuse me. All right. So again, I want to use I'm going to use this angle 33.32 degrees. So step 3 here, I'm going to use that angle again, and I want to relate it to the adjacent side, this unknown x, and the hypotenuse. So cosine relates the adjacent to the hypotenuse, so that's what I'll use. Cosine of 33.32 degrees is equal to our adjacent side x divided by our hypotenuse 53.58. I'll write in the same step we've been doing. I'm going to multiply by the 53.58 without skipping a beat. You'll probably get really used to doing this because you'll have to do it a lot. Multiply by that denominator, 53.58. And that will eliminate this. Okay. So that gives us x equals well, this cosine times 53.58. $53. I think I just may have typed this. Oh no, that's my other angle, 56. Okay, never mind. Getting confused here because my 3 is so messy. So that is correct. This was where my 6 is up here in the angle. So let's see, 53.58 times cosine of 33.32. All right, and I get that that is 44.77229. But again, we only want 4 significant digits in this problem, so that's our 44.77. Looking at the 2, the next number, this 2, that's less than 5, so we don't need to round our 7 up. We just leave it as a 7. So our answer here for this side is 44.77. Now we have all 3 sides. 1, 2, 3, and we have our 3 angles. So we have officially solved this right triangle. Okay, so the very last thing in this section is angles of elevation and depression, and we're going to use this to do a more exciting word problem than what we've done before. So these are angles measured from a horizontal line. So if you're looking off at the horizon, you know, if you're like you've got this horizontal line parallel to the ground, then the angle you're looking up at, like if you have to look up at something, that's your angle of elevation. That thing is elevated, so you have to look up at it. If it's below you, that's an angle of depression. You have to look down at it. So if you're looking below the horizon, it's an angle of depression. If you're looking up, it's an angle of elevation. One other thing, a lot of word problems, and I've seen a lot of these over the years, just a tricky little tidbit there. You're going to have to take into account where you're measuring from. And the example I give you does this, so you'll get to see exactly what I'm talking about. Example 3, Pat Porterfield knows that when she stands 123 feet from the base of a flagpole, the angle of elevation to the top of the flagpole is 26.3 degrees. Wow, Pat, how do you know that? To be fair, there are ways of measuring that. You could use a sextant, for example. So she knows this angle is 26.3 degrees, and that is conveniently labeled for us in this diagram. What else? Her eyes are 5.3 feet above the ground. Find the height of the flagpole. And this is what I was just mentioning. You have to take into account where she's measuring from, because the height of the flagpole is going to be this length of our triangle, but then you'll have to add in her height, or the height of her eyes, to get the total length. Because she's not measuring this 26.3 degree angle from the ground, she's measuring it from her eyes. So this is really nice. We're just going to look at the right triangle portion of this, and we're going to ignore the 5.53. So I'll just draw a big circle around that. And just remember, at the end of our answer, whatever we find for this length A, which is the important one, we're just going to have to add it to 5.3 to get that extra little piece of the flagpole. So we're going to calculate this using trig rules, and then we're going to just add on 5.3. And this should be pretty easy to do. They're not asking us to solve the whole triangle, thankfully. We're just being asked to find this unknown height. The question is, how can I relate an angle to the side opposite it? And the other bit of data they gave us. They gave us this 123 feet, and where is that? For those of you playing at home, yes, that's the adjacent side. So we're trying to relate this angle to the opposite and the adjacent side. So that would be tangent. So I'll go ahead and write the tangent formula, or the tangent definition, while plugging in the values that we know. So tangent of 26.3 degrees is equal to A divided by 123 feet. Hopefully you're getting really comfortable with this because you're going to be doing it all semester. Probably the most common calculation, multiplying with that denominator to move it over to the other side and get it away from our variable. Get rid of this since we're multiplying and dividing by 123, and leaves us set up to do this all in one step. Yay! So let's see, 123 times the tangent of 26.3. 60.79 and a bunch of other decimals. 0.39. Okay, so let's see. We have 3 significant digits here. We have 1, 2. Do we count this 0? Yes, we do, because it's to the right of the decimal place. So again, we have 3 significant digits. And 123 feet, 3 significant digits. So they all have 3 significant digits. This should have 3 significant digits. So let's see, that would be the 60.7. That's our 3 digits. We're counting the 6. We're counting this 0 because it's between 2 other digits, the 6 and the 7. And the 9 tells us we have to round up that 7 to an 8. So our length A, or our height A, is 60.8. What are we working with? Feet? Yeah, feet. So A is 60.8. But don't forget, we have to add that. We only found, this thing does not like me doing that. We've only found this length. We need to add it to our 5.3. So we add that. And we get 66.10. And again, we want to write that as 3 digits of just 66.1 feet. And we've done it. We found the height of the flagpole. And with that, we have finished section 2.4. So if you made it this far, congratulations. Sorry I've rambled for so long, but thanks for coming, and I'll see you next time. Just kidding, you have to sit here and watch me try to figure out how to close this program. Do I want to make changes? Nah. Oh, there's the little bar. Oh, screen recorder. See, like this little toolbar would be nice if it didn't hide it.